Everybody, just a few housekeeping items as we go into our session. As you know, we record these, and so recognize it's a week of many vacations here in late August. So many of you are going to be viewing this on NAWI's YouTube channel. So that's why we record these things. I will invite you to put your comments and questions into the chat as we go along, but I'll keep you muted. And at the end, we'll have a Q&A session. We'll likely unmute people who write questions. And so that's how we'll kind of do this. You can also use a raise hand feature once we're in the Q&A section. And then, audio issues happen. They happen to the best of us. All I can say is, well, we wish you well, but there's always the recording. So if you miss a bit, you can always catch up there. Finally, I kept the cost share in. We continue to benefit whenever you register cost share hours with the NAWI program. So at the end of the webinar, we'll have a link for you to drop in your cost share hours. Just register for the hour from us, and we get cost share credit from the Department of Energy. Isn't that nice? And then if you aren't already following us on LinkedIn, our LinkedIn page is now one of the major ways in which we announce webinars and other activities, so do check us out there. All right, well, Carl and Tony, the subject of today is your area of expertise, which is tanning booths. No, it's not. It's UV disinfection. And in fact, ultraviolet light and ultraviolet diodes is an extraordinary branch of technology that really, as this technology grows and matures and gets more and more powerful, the potential for utility in water treatment becomes greater and greater. And there are no two better people we could have for this hour to talk about the frontier of utilization of UV diodes and UV light for water treatment than Carl Linden and Tony Straub. Carl is the department chair. Are you still department chair?
Yes, I am.
Oh, you have my
Amazingly.
sympathies, buddy. Okay. But and Carl's been one of the long-standing real leaders in the area of UV light for inactivation of pathogens and also driving chemical reactions. You were the Clark Prize winner in 2020, and then you just were awarded the AP Black Award from the American Water Works Association and gave a lovely talk in Denver, and we're looking forward to hearing some of those same themes today. So Carl is the department chair. Suffering at the top and suffering at the bottom is Tony Straub, assistant professor in the same department. But Tony is a wonderful, friend of you. Both of you have been longtime active researchers in the NAWI program. But Tony, you are now assistant professor in the same department with some your background and experience at Yale, University of Illinois, and MIT. And very complementary, you also work on design of materials and processes with a particular focus on membrane technologies and interfacial phenomenon. And of course, light impinging on a surface will create stuff at interfacial, interfaces. So, gentlemen, thank you so much for joining us this hour. And I'm going to stop sharing and invite Carl and Tony to share their slides and begin our presentation. Thank you guys very much.
Great. Thank you so much, Peter. Appreciate that. Thanks for the introduction. Looking good?
Looks great.
All right. Super. Yeah, our talk today is really describing the work we've been doing on our project that's funded through NAWI. It's looking at a new branch of UV technology that centers around emissions at 222 nanometers, which is a little bit different from the traditional UV technology. And we're looking at that to drive advanced oxidation and disinfection, and specifically looking at that for pretreatment of membranes and reducing fouling on those membranes. So that's where the combination of Tony and I come in, both working on the UV side and the membrane side, and this collaboration really has helped to move the field forward in quite a few interesting ways, which we're excited to share with you today. Our team is quite large. At the University of Colorado, myself and Tony are the PIs here. We've got a number of doctoral students, Emma Payne and Tricia Nickerson, postdoc Dana Pausty, and a couple of master students, Emma, Josh, and Jacqueline. And then at USC, we're also partnering with Dan McCurry. Dan's been leading up our chemical analysis and looking at some disinfection byproducts that we'll be getting into in this next year of the project. And he's got a couple of students, Hatian and Zhao as well. We really appreciate support from our industrial partners like Ushio and also our utility partners listed there. So the objectives of our NAWI project overall are to look at the extent of RO fouling mitigation that we could possibly achieve using actual wastewaters and with practical UV treatment scenarios that are typically used in water reuse. We're also trying to evaluate organic contaminant destruction and virus reduction because those are two key parameters for water reuse applications. So things like 1,4-dioxane and virus, reduction, 4-log virus, 6-log virus. We want to also look at the fundamentals, obviously, of this process too. We're researchers. We want to know why what we're seeing is happening. Looking at the radical generation we're able to achieve with these different types of UV technology, how the water quality impacts those things, and what byproducts might be forming. And we also want to look at scale up. We've got a flow through system running now with the 222 technology. We're really excited to share some of those results with you as well. And then eventually looking at the economics, and we have some preliminary economic data to share as well today. So you may all be familiar with conventional water reuse situations, and just get a little pointer up here. Traditionally, we have this kind of standard technology suite that takes wastewater effluent, goes through a membrane process for separations, and then reverse osmosis, really removing a lot of those contaminants. And then it goes through a step of UV advanced oxidation that adds hydrogen peroxide to the system and typically uses conventional UV sources, which is a mercury vapor lamp emitting at 254 nanometers. And that's conventional. What we want to do in this project is kind of flip that convention on its head and put the UV actually in front of the RO membrane to see if we could help mitigate fouling on the reverse osmosis membrane and look at this specific technology around 222 nanometers because we feel like it has some unique advantages above the 254 technology, which we'll be talking about throughout the webinar today. A little bit of background on UV disinfection. Mechanisms for UV specifically, UV is a photolytic process. These photons pack energy and wavelength, and basically we have to absorb the photon to create any kind of photochemical effect. So if the photon's not absorbed, there's no photochemistry happening and light doesn't do anything for us. But in the case of disinfection, the target typically is nucleic acids of an organism, and the DNA of an organism typically absorbs in this fashion. We have wavelengths from about 100 to 400 nanometers is the UV spectrum. And this little graph here, which I'll show a little bit more detail later, is the absorbance of nucleic acids. And you can see kind of that sweet spot of a peak around 254 as well. And that wavelength gets absorbed by the nucleic acids and nucleotides, creates damaged sites on the DNA, and basically ties the DNA up in knots and creates things like thymine dimers and other types of damage, and it prevents that organism from replicating. And any organism with nucleic acids, which are, of course, all organisms, will have this effect. So it's great for bacteria, viruses, and protozoa disinfection. In fact, one of the drivers for UV is actually it's really effective for Cryptosporidium and Giardia, which are known to be very resistant to chlorine disinfection. And that's really driven the adoption of UV across water treatment processes worldwide. One of the initial motivators for this work is the work we did on virus inactivation. We had this unique opportunity to work with NIST, the National Institute for Standards and Technology, that had a UV laser, and they had a laser that was able to emit wavelengths at different unique outputs along the UVC spectra. So 210 at 220 at 230. We're able to study each of these wavelengths individually and look at virus disinfection specifically. What we found with adenoviruses is just one of those kind of hard to kill viruses for UV. Compared to 254 inactivation, the effect of the wavelengths as you get lower and lower was really compounding. In fact, we see that wavelengths down at 220, 210 nanometers are almost up to 20 times greater for inactivating this virus than 254. And this really drives some of our thinking on can we introduce these lower wavelengths to help enhance virus disinfection and enhance UV treatment and affordability and effectiveness. So the drivers there are looking at again, photochemistry has to happen. The wavelengths the photons have to get absorbed. In this graph here, I have the absorbance again of DNA, and this is wavelengths from 220 down up to about 300 nanometers. And have the absorbance of DNA here, and then the absorbance of proteins. This is kind of a generic protein absorbance curve as well. I'm thinking here about viruses, which are really unique organisms. They're basically nucleic acids surrounded by a bunch of proteins. They're really not technically alive. They don't actually have metabolic processes going on. So we think of them as viral particles. But the proteins are really interesting here because the proteins mediate the infectious process. So these little fiber proteins, they go out and find the host cell, they attach to it. The virus then enters the host cell through the mediation of these proteins. And is able to take over the host cell machinery and reproduce itself in that host cell. They're quite amazing creatures, actually. But thinking about these two mechanisms, genomic damage and protein damage, looking at wavelengths around 254 to 265, we see this peak of DNA absorbance, and those are really the sweet spot for nucleic acid damage. And there we see also the wavelength at 254, which is really specific for nucleic acid damage and these kind of genomic damage. What we see with proteins, the absorbance at 254 is actually kind of at the low point for absorbance. And we see really high absorbance at the lower wavelength, especially around 220. And that's where this wavelength at 222 comes in, because it could damage the proteins in a way that the 254 cannot. And if we could damage the proteins, we get much more enhanced inactivation of viruses specifically. We don't see this effect as much for bacteria. We see them about equal effects. But for viruses, protein damage is really, really important. And the 222 is really effective for inactivating viruses by that mechanism. But to keep that in mind as we go through some of the other slides here. The other motivation here is some of the work we did looking at conventional UV applications of advanced oxidation that use UV hydrogen peroxide. And what I show here is the absorbance of hydrogen peroxide, the mole absorption of hydrogen peroxide here in this curve here, and down to from 200 to about 300 nanometers here. And I showed the emission spectra of the 254 and the 222 lamp. And again, basic photochemistry, you can see the 222 absorbs less. The peroxide absorbs less at 254 than at 222. In fact, it's about 5 times higher absorbance at 222. What that results in is higher radical production because of the photochemistry. Again, the more photons absorb at that 222 wavelength. And for the effects on things like carbamazepine and NDMA, we see about 4 to 5 times increased degradation rate under 222 nanometers compared to the conventional UV. And that's both driven by hydroxyl radicals as well as the direct UV photolysis of the NDMA. And this work was really interesting to us. We furthered this work by thinking about nitrate. And nitrate's really interesting here because nitrate's often present in contaminated groundwaters and certainly in nitrified wastewater effluents. And you'll see in all the wastewaters we use from our partners, they have 3 to 8 milligrams per liter of nitrate in them. And the interesting thing about nitrate is, first of all, it's highly absorptive down at 222, where it's not barely any absorption at 254 in this curve here. And you look at, this is the absorption of hydrogen peroxide way down here. So the absorption of nitrate is, orders of magnitude higher than peroxide. So peroxide 254, we get 21 absorbance, we get about 100 absorbance at 222. But for nitrate, the mole absorption coefficient is almost 3,000. And this really drives photochemistry, because photochemistry of nitrate with UV light will form OH radicals as well as reactive nitrogen species at a rate that's comparable to hydrogen peroxide photolysis. This is really exciting for us because we think we can use this in situ nitrate with the 222 technology to produce radicals and destroy contaminants without ever having to add any peroxide, which would save a great amount of costs for utilities. This is a basic simplified mechanism of nitrate plus UV light forms these hydroxyl radicals. It also forms some nitrogen radicals as well, which also can do work for us and help us out for degradation. So we published this work in a paper back in ESNT Letters. What I'm showing here is basically the production of OH radicals normalized by the radiance, by the intensity of light under these different scenarios. So how much radicals you can produce under low pressure hydrogen peroxide, krypton chloride 222 hydrogen peroxide, and krypton chloride nitrate. What we found here is we have about 13 times greater production of radicals that under the krypton chloride nitrate than the low pressure system. We have about 1.5 times greater in the nitrate system than even using krypton chloride plus peroxide. And we see in groundwaters and authentic waters, we see that still being the case, even though we have a lot of radical scavengers that are also in the water. This work is really driven by the high absorbance of nitrate, and these performance benefits we think will carry over into wastewater treatment, which is what we'll show in a few minutes here as well. We published this in ESNT Letters. This is one of the first papers I got this information out into the literature. Really proud of this work we put out. This is actually right at the time we were putting together our proposal for NAWI, and it was perfect timing to produce and present this work as part of our proposed research. So the outline of what we'll talk about today as far as our NAWI project goes, we're going to go through some of the virus and bacteria disinfection work that we've done, look at the contaminant destruction work we've done, of course, get to the fouling reduction, which is the key outcome of this research, is can we reduce the cost of RO treatment with putting UV treatment ahead of RO, and then looking at opportunities for technology scale up as well. So the overall approach to our research, we have 3 partners for municipal wastewaters. We have other partners we're looking at also for produced water and other types of water as well. But we're talking about the 3 wastewaters specifically for wastewater reuse applications. And with those wastewaters, we subject them to different types of UV treatments. Of course, no UV treatment as our baseline, the 222 UV treatment, and then the 254 with peroxide, which is a standard kind of approach for water reuse applications. And then we're going to evaluate the performance of those treatments on virus bacteria disinfection, destruction of contaminants, as well as reduction in fouling. So we'll talk through each of these areas. So the 3 wastewaters we have are quite different. We have one wastewater that we call indirect potable reuse, because that's a wastewater that's taken from actually an effluent that's run to a natural water body. And then this is a water utility that picks up that wastewater impacted river, goes through bank filtration, aquifer recharge, softening. So that's a unique characteristic of that wastewater, is that it has that kind of treatment ahead of it. We have a wastewater coming from a municipal system, which is typical secondary effluent of activated sludge. We're taking that pre-disinfection. And keep in mind, these results we're showing you, these are actual wastewaters that have just treated by secondary effluent to the secondary effluent standards. They're not treated yet to high levels of treatment, like through membrane processes, for instance. So it's really unique that we're using these waters that are pretty dirty and pretty unique to a water reuse situation that we can treat at this stage. The third wastewater is a municipal wastewater effluent that we take pre-chlorination and before the MFRO process that they use. And you'll see the range of TOCs we have here, organic carbon concentrations from 3 up to 7, different levels of UV transmittance of the waters, different nitrate levels from about 2 to 8, some nitrite as well. Alkalinity is fairly decent in all these, which creates a radical scavenging effect, and the different pHs. So quite a diversity of wastewaters, and you'll see the different results that we came up with based on these different water qualities. So first is some inactivation data. So this is virus inactivation. We use an MS2 coliphage, which is kind of the standard surrogate that's used to evaluate virus disinfection in UV systems. This plot here basically shows the 3 different wastewaters we have. And the fluence levels here, the UV doses that we're showing here, are the doses required to achieve 4 log reduction of viruses. And in the dark blue, we have the 222 results. The light blue is the 254 results. And the lower doses is going to be better treatment because it takes less energy to achieve that 4 log. What we see here is across all these effluents that the 222 treatment requires much lower dose than 254 to achieve that same 4 log. It's about 2 to 3 times faster in activation than 254. And again, that's driven a lot by that virus protein absorption at 222 I talked about earlier. We look at our bacterial inactivation results. We've done a bunch of different bacteria as well. This shows the results for Pseudomonas, which is one of the problem bacteria in biofilms and such, and fouling. And you look at these data here, again, the different wastewaters, and again, it's the fluence to achieve 4 log reduction. First thing you notice is the fluences are much, much lower. We're talking about fluences less than 10 millijoules per centimeter squared, where for viruses, we're at 40 to 100. So bacteria are much more easy to kill than viruses with UV. So regardless of that low fluence, though, we don't really see much difference between the 222 and the 254 treatment. And that's, again, because this is really driven by the DNA damage for the bacteria rather than the protein damage. So that 222 doesn't really give us much of an enhanced effect that we see for the viruses. And this is really a unique difference between the bacteria and the virus disinfection under 222 and 254. Regardless, we get both situations, we get excellent disinfection with UV. And these doses, again, are about 10 times lower than you typically use for advanced oxidation processes. So we're doing totally fine here for inactivating 4 to 6, 8, 10 log probably viruses, if we can even measure that high. For the destruction of the contaminants, first we'll look at NDMA. NDMA is N-nitrosyl-dimethylamine, which is one of the target contaminants of a lot of water reuse situations. This data shows the degradation rate constant, so a higher rate constant is better in this case. Again, we have the wastewater partners here, 222 in the dark bars, 254 in the light bars. You'll see for all the wastewaters we looked at, the NDMA degradation under 222 is about 3 to 5 times faster than under 254. And this is driven mainly by direct photolysis, because the NDMA, as I'll show you in a little bit, has really important absorption features, and here's that data. So this is the absorption of NDMA from 200 to about 300 nanometers. This is the NDMA absorption here. And you'll see that peak absorption really around 225, 230. So that 222 sits right in that peak area. And again, the fundamentals of photochemistry, you have to absorb the light to get a photochemical effect. Of course, there's less absorbance at 254. 254 actually works great for NDMA as well. It's still pretty decent. It's almost 2,000 mole absorption coefficient, but at 222 up to about 8,000. So it's quite unique in that fact that 222 goes much faster, about 3 to 5 times faster than the 254. And that's again driven by the molar absorptivity of NDMA. And the fact that NDMA degrades primarily by direct photolysis. It doesn't really degrade much by hydroxyl radical production. If it did, we'd see that effect here, but that effect is pretty much ignored here because most of the degradation is due to direct photolysis. The next contaminant is 1,4-dioxane, and unlike NDMA, 1,4-dioxane basically doesn't absorb light at all. It only is driven by OH radical-based degradation. So similar here, we have the degradation rate constant here. And again, the higher rate constant, the better, the faster it's degrading. We have the 3 wastewaters, and we have the 222 in the dark bars and 254 in the light bars. This 254, keep in mind, is UV 254 plus hydrogen peroxide. So we're adding peroxide at typical doses that are used for water reuse. And even when we put the peroxide into the 254, using 222 alone still outpaces the 254 by 4 to 10 times. We get that faster decay. I mentioned before there's not much absorbance, so why do we have that better treatment? The OH radical rate constant for 1,4-dioxane is pretty high, so it'll go fast when you have production of radicals. We certainly get that production with the UV 254 hydrogen peroxide, but what we have in these cases is we have that nitrate present in the wastewaters, about 3 to 8 milligrams per liter, and that nitrate gets absorbed. The photons get absorbed by that nitrate at 222, and they produce those hydroxyl radicals. And so in effect, we have this what we call a de facto advanced oxidation, where we're not adding any peroxide, just using 222 and the native nitrate in the water, and we get better treatment than if we added 254 treatment with the peroxide addition as well. So we find these results really compelling and a really good argument for looking at the enhancements we can expect with 222 treatment. I'll move on now to some of the work we did on looking at organic matter transformations. And we think about fouling on membranes, we think about organic matter as one of the main foulants. So we wanted to characterize the changes in organic matter. And again, this is a wastewater effluent organic matter that are naturally occurring in these wastewaters. And we're studying them using tools like fluorescence, which is excitation emission spectra. Here, this colorful picture here, we can pick out different types of peaks. In this case, we have the degradation of this peak B, which is a protein-like fluorescence. And we look at the degradation of this peak, which tells us how this organic fraction is degrading under 254 peroxide as well as 222. We see enhanced degradation of this peak under 222. This is just an example of some of the data we've got. We also look at a tool using size exclusion chromatography coupled with TOC analysis. And in this case, we produce these curves that have these kind of elution curves that indicate as the water comes off of the column, in this case, the larger molecular weight fraction comes off first, and the smaller molecular weight fraction comes off later, and it comes off over time. And what we see is for different levels of treatment, we see a decrease in this large molecular weight fraction as we increase the UV treatment with 222, and we see some intermediate weight fractions kind of growing a bit as those larger ones degrade, and we see some indication of formation of smaller molecular weight compounds too. And this is really important to understand related to fouling, which we'll get into in the next slide as well, and as well as when Tony starts his presentation. So again, we see that decrease in the large molecular weight fraction as we increase the UV treatment. Looking at our partner waters more specifically using this SEC TOC approach, this is our indirect potable reuse water and our 2 wastewaters. This IPR water is really interesting because it actually doesn't have any large molecular weight organics. Because it went through that process of, it's in a river, it went through bank filtration, it went through aquifer recharge, we almost lost all those large molecular weight organics. So it only has some of the medium molecular weight organics. And you see with increased treatment, we see that peak going down a bit. Looking at our wastewater, we see this large molecular weight organics here, again, going down, and we see an increase in some of the smaller molecular weights. And we really see that quite a lot here with our wastewater too. So these size exclusion chromatography results are able to demonstrate like how the molecular weight characteristics change from larger to smaller under different UV treatments, and how that we can look at how this change might impact the fouling of membranes that are downstream of our UV treatment. This is a really powerful tool. We've got tons of data like this, and we're working on a few publications that will help show everybody what we've been working on. One of the things we also want to do is look at how efficient are these two processes. We know that they're very different. The 254 has been around for over 100 years. It uses a conventional light-based process. The 222 is an excimer-based process. That's a different process that has different drivers. What I'm showing you here is data that's called the EEO, which is electrical energy per order. It's basically how much energy it takes to degrade one order of magnitude of a contaminant in 1 cubic meter of water. And we have comparisons of 254 and 222. 222 is in the light bar, 254 is in the purple for NDMA and 1,4-dioxane, and for our 3 different wastewaters that we looked at here. And basically what we're showing here is that the lower energy, the better, because we want to use less energy. That saves energy. Higher energy, the worse we have. What we find here is that we really see very similar electrical energy usage between the two systems. And that's really different for a number of reasons. We know that I just showed you the 222 is much better at degrading these two contaminants, 2 to 5 times better. But the challenge here is the efficiency of the current technology for the krypton chloride technology is about only 10%, and the low pressure UV lamp is about 35% efficient. So the wall plug efficiency is quite different. Low pressure is much better. Krypton chloride is still in its infancy, really, and as far as technology goes, it's only been around for a decade or so versus over 100 years for the low pressure technology. But even so, with these differences in efficiency, we see the EEO is very, very similar and comparative. And this is really exciting data for us because this shows that the efficiencies that we see in the 222 process and the potential to even not use peroxide. Remember, these costs actually don't even include the savings that you'd get from not using peroxide. So this is just the energy use, and you'd have increased savings from not using peroxide as well if you had that nitrate present. So that's really interesting data as well. And we're getting more of this data as we work on our pilot-based systems. So with that, I hand it over to Tony to talk about the membrane fouling testing and get into some RO membrane work.
Cool. Thanks, Carl. So as Carl mentioned, one of the main goals of this project was to see whether or not UV treatment could effectively help mitigate fouling in a wastewater reuse scenario. And so for the membrane fouling testing, we took source waters. We used the 3 wastewater effluents or wastewaters that Carl mentioned. We also used model foulant solutions to kind of better understand some of the mechanisms of fouling. And then we used the same kind of pre-treatment and UV treatment that Carl mentioned. So a no UV control, 220 nanometer UV, and then 250 nanometer UV plus peroxide here. We did reverse osmosis testing for fouling here. We were limited in our feed volumes that we were using. And so we just did a dead end fouling test here. And so you can see this is a dead end stirred cell. And during operation, what we're measuring here is the flux, the salt, and the TOC rejection to check on membrane integrity. After testing, what we did was we looked at water quality parameters. So we looked at the organic carbon profiles with size exclusion chromatography and TOC. And then we also looked at the morphology of the fouling layer with SEM, AFM, and then we also looked at the chemistry with XPS and EDX. Next slide. And so a lot of our testing focused on the wastewater effluent stream. So this is wastewater 1 from Carl's previous slides here. This is kind of our representative wastewater effluent. And here I'm showing the fouling results with different UV treatments. And so the y-axis here is showing the flux decline, just percent flux decline. The first curve here is no UV treatment. That's kind of our baseline. And then we have the different UV 222 curves here. And the second number after 222 is indicating the fluence. So we have higher fluence going to the right here. And then we have the UV 254 results here on the right, again, with different fluences. And then the last column here is with a higher peroxide concentration. And so what we could see here is that we saw decreases in the level of flux decline with both UV treatments. But with UV 222, we saw a greater decrease in flux, so better fouling mitigation with UV 222. And this was somewhat dose dependent here. And so if we could get up to about 60% fouling reduction with this 400 fluence here. And as we went to higher fluences, we saw that flux reduction didn't necessarily get better. UV 254 got a little bit less fouling reduction, but still showed reductions in fouling. One important thing to note with this data is that we have kind of another baseline that we would have. We are running these systems to 75% recovery in the fouling unit. And so if we only took the TDS of our wastewater and ran it to 75% recovery, this is about the flux decline that we would see. And so in the best case, in the best fluence for UV222, we're getting fouling reduction that would almost correspond to not having organic matter fouling in our solution here. We wanted to understand the nature of this fouling better. As Carl mentioned, we did size exclusion chromatography to look at the different feed solutions that we're using for fouling. And one interesting thing we saw, this is showing the degradation of the TOC in the fouling solutions with UV222 and UV254 at different fluences. And so with UV222, we saw degradation of the high molecular weight species, that first peak Carl showed, but we also saw degradation of the lower molecular weight species in most of the cases here. For UV254, we did see degradation of the high molecular weight species, but we saw less degradation of those lower molecular weight species. And so we think this has to do with the improved fouling performance that we saw with UV222. We also used SEC to look at different kind of characteristics of the organic matter. And so these kind of three different plots are similar to the last one, but they're showing different absorbance or fluorescences that would correspond to aromatics, protein-like compounds, and humic-like compounds. And the general takeaway from this is you're seeing UV222 again on the left here, and the UV222 is getting higher degradation of each of these classes of compounds compared to UV254 with peroxide. One thing that's important to emphasize with our kind of fouling studies is that the fouling reduction really depends on the nature of the feed water and the nature of the organic matter that's in the feed water. So this is our flux decline testing, our fouling testing with the IPR water that Carl showed. This is the water that generally had lower TOC and didn't have any high molecular weight organics in it. And so with this water, we generally saw lower levels of fouling. We saw a different optimal UV fluence to mitigate fouling, but we still did see improved performance of UV222 compared to UV254 in terms of being able to mitigate fouling. And then the last wastewater we tested was quite interesting. This was the second wastewater. And what was interesting about this water is that it had a higher concentration of proteins in it and higher TDS. And what we noticed with this water, which is quite surprising to us, as in this case, the trend reversed, and UV222 actually made fouling worse in the system. And we can see from the SEC data, what's happening here is the organics in this wastewater specifically, the high molecular weight organics are being degraded, but we have negative degradations. We have production of medium and low molecular weight organics in this system. And so this means that these proteins are likely being broken down into smaller organics that actually make fouling worse with UV222. And we didn't observe this kind of same phenomena with UV254. To get an even better idea of what was happening here, we tested fouling with model organics. And again, these model organics really showed that the nature of the fouling waters is quite important in terms of fouling mitigation with UV. So for humic acid, you can see here UV222 did effectively improve fouling here. But for the other two foulants that we tested, bovine serum albumin, which is a model protein foulant, and alginate, which is a hydrophilic gel-forming foulant, we actually saw worse fouling with the protein and not much of a change with the alginate here. And so again, this kind of emphasizes, as we saw with the second wastewater, that protein fouling is not very effectively mitigated with UV222, but with humic acid and other types of organics, it is quite well mitigated. The last kind of fouling results I'm going to show here are just microscopy results from the fouled membranes. We did a lot of work to characterize the nature of the fouled layers on the top surface of the membrane. And so here I'm just showing images of the different fouled layers with our wastewater 1. You can see this is the left is the kind of control, UV254 and UV222. And one kind of interesting thing we noticed in a lot of our fouling testing was the actual structure of the UV222 fouling layer appeared to be quite different. Here you can see it has smaller particles and it tends to be more porous than that from the untreated or UV254 treated water. We did an additional characterization with SEM EDX and also with XPS. And both of those basically showed that we're seeing an increase in the kind of oxygen groups on the surface of the fouling layers. And so we think this kind of matches a picture where we see these organic matter are, breaking down They're becoming very hydrophilic, and so they're forming these very porous kind of gels on the top surface of the membrane rather than more dense structures. And so, yeah, we saw more porous, less dense structures, and more oxygen in particular in the UV222 samples.
Thanks,
Cool.
Tony.
Yep, yep. Handing it back to Carl.
So I'll talk now about some of the scale-up considerations we're looking at. We're just developed and been testing a flow-through reactor design. It's very, very primitive, I'd say. We're just putting lamps basically on top of a serpentine track of quartz tubing. So we designed this system to optimize the UV222 output of the lamps that we have, and we can treat about 100 milliliters per minute, which is kind of our target range that we hope to do to investigate some scale-up issues. Basically, this will help facilitate some economic analysis, some electrical energy efficiency data, which we're just generating now. What we've done in this system is we've done the tracer testing, we've got the hydraulic characterization using all the kind of standard environmental engineering practices for tracer testing. We've determined the fluence we can deliver in the system at different flow rates and with different numbers of lamps on or off and at different power levels for those lamps. So each of these lamps can run at different powers, so from 20 to 100%, and we could put on either 1, 3, or 5 lamps at a time to get a range of different fluence levels, and we can test the different flow rates as well. With this kind of matrix of kind of levers we have to pull, we can get a full range of UV fluences that we can deliver in the system and test out virus disinfection and contaminant degradation. We've done some great analysis already on this system using a chemical tracer called perichlorobenzoic acid, and we've seen some really good results for production of radicals, both under UV peroxide plus doing the work with direct wastewaters like we had showed you before with the nitrate-driven OH radical production. So we're working on evaluating both NDMA and 1,4-dioxane in this system as well, and we'll be able to generate those electrical energy numbers. And again, this kind of integrates the hydraulics into the electrical energy, which is a very primitive system. It's not optimized. It's not similar to other systems you might see, but it'll give us a first benchmark on how well we can consider the scale up for the 222 base treatment. So thinking about what we're doing in our project, we have this conventional water reuse treatment train. It uses microfiltration, ultrafiltration, then followed by reverse osmosis, and then this UV254 hydrogen peroxide. And again, we flip this around and put the UV system ahead of the RO system. We've got our 222 technology that doesn't use hydrogen peroxide. And what we found is we can achieve very high levels of virus reduction, 4+ log easily. We get really efficient decay of NDMA, which is one of our target contaminants. We have great production of hydroxyl radicals just from the nitrate that's native in the water that can drive treatment for hydroxyl radical-based degradation. And we don't have to add any hydrogen peroxide. And we also see in many cases we can significantly reduce the fouling and reduce the cost of running reverse osmosis treatment. So we're really excited about these results. We're continuing on the next couple of months, and as we wrap up our project with NAWI, we've also been considering what is our ideal kind of future treatment look like. Obviously, the 222 technology is great. 254 is also great. I mean, it's great for disinfection. It's been out there for a long time. We've been working with a lamp manufacturer to consider a new kind of next generation UVC lamp technology, and that really is run by this phosphor type lamp that emits at a xenon excimer lamp that emits at 172 nanometers inside this lamp, and the lamp's covered by this phosphor coating, and the phosphor absorbs the 172, and due to its proprietary nature, it emits at a really unique spectra, and it provides us some really unique spectra we can think about using in the future. We just started working with this lamp. This is the kind of a new technology. We just connected with this professor at Rutgers University who's developed this system, and we're testing this lamp in our lab now. And basically what the really interesting part is that the spectra that we're able to achieve with this lamp takes advantage of the low wavelength 222 areas, but it also keeps us with the UV 254, 260 range that we know is great for disinfection as well. But we'll also have that kind of nitrate-driven process perhaps with this lower wavelengths. So this kind of dual wavelength emission is pretty much our ideal kind of manifestation of a UV system if we can think about combining all the work we've done. And we're really excited to test this system out. We hope maybe in a NAWI 2.0 project we can help to test this out a little bit more and see if we can push this lamp out for more testing and perhaps in a treatment system in the future. But it's got pretty high output compared to the krypton chloride eximers, and the electrical energy is quite high, more so around the level of a low pressure lamp compared to the 10% that we see with the krypton chloride lamps at 222. So really excited about this technology. I hope to be able to share more with you about this soon. So what are our next steps in our project? Basically, we're working to characterize an activation due to some of the reactive oxygen species and the reactive nitrogen species. So we want to see what role do these oxidants play in disinfection. So can we enhance virus disinfection through these reactive nitrogen species we know we're generating under the UV nitrate process? We're looking at biofouling now. We showed you a lot about organic matter fouling, but we've shifted our work to looking at biological fouling and what is the impact of UV treatment at 222 versus 254 on biological fouling of the membranes. We're working quite a lot with the USC group on contaminant fate under a 222 chloramine advanced oxidation process. We didn't talk much about chloramines, but chloramines also absorb UV light quite well at 222, and this combination can produce an advanced oxidation-based process with radical formation, both chlorine-based radicals and hydroxyl radicals. So we're looking at this process. It's been looked at with some other groups as well, but we're studying it under our waters with our 222 lamp. Similarly, we're going to be looking at some formation of any byproducts or unwanted products that are forming following the UV treatment. We've got our bench scale flow through characterization that's ongoing, and we're going to be evaluating this new dual wavelength UV system. And a side project as part of the add-on funding that we got recently, we're going to working with Professor Sedlak at UC Berkeley, where he's developed an electrochemical production of peroxide and chlorine, and we're going to couple that with our UV flow-through system and see if we can work these two technologies together to treat premise scale water reuse systems such as gray water and on-site black water systems as well. That wraps up our presentation. We're happy to take some questions, and we really appreciate your attention. And thanks. Over to you, Peter.
Guys, thanks so much. That was great. And dude, that new lamp looks really interesting.
We're really excited about it, definitely.
So,
Wanted
and
to
then
give you a
maybe
sneak peek.
we got a couple, I've got one question, Adam and T has a question, but I want to start maybe with that lamp at the end and maybe talk about lamp technologies in general. So the 222 lamp, why was it invented? Can you tell us a little bit about the context for UV light sources? In other words, are they invented? They're not invented to drive efficiency in water treatment. The technologies are being driven for other things. So my first part of my question is, what is driving some of this UV light innovations? And secondly, can we expect a continued kind of like a steady march of higher energy, lower frequency, more diversity in kind of a wavelength structure? So tell us a little bit about the sources.
Yeah, thanks, Peter. That's a great question. Our initial interest in the 222 lamp was, we had this data that we generated with that NIST laser, which obviously is not practical to have a laser treating UV, treating water.
Yeah.
But we were looking for a source that would produce a clean output at the lower wavelengths that we could study for virus disinfection. We found this excimer source that was kind of in its infancy in the early 2010s. There had been a lot of work in Russia actually on this with this excimer source, but what's really driven it in the last 3 to 5 years is the pandemic. Because 222, it turns out, is quite safe to use in the presence of people. Like, it doesn't actually damage your skin at the same level that 254 does. And the reason for that is that, actually, I've got a slide here that I could show you, but the reason for that really is because these wavelengths don't penetrate the skin very far.
Interesting. Yeah, okay.
They're so highly energetic that they get absorbed literally in the top few micron layers of your dead skin cells, and they don't get into the deep basal skin layer that 254 does get into. So that's driven a lot of the interest and production and actually commercialization of these 222 sources. Okay. So of course we did some of this work too during the pandemic, looking at virus disinfection. We did SARS, we did flu viruses, all kinds of things. Yeah. We found high effectiveness for this 222, but we said, what if we try to use this more for advanced oxidation? We know the protons are there. We know they get highly absorbed. So that really drove our work here.
Okay. So for the 222, this was essentially for surface disinfection and sort of public health. That's the kind of industry that's driving this forward. So the second part of my question is, you were talking about how the 222, plug efficiency is lower, but can we expect that a steady march in plug efficiency, or do you know now that the krypton, kind of system is kind of where it's going to be, and you're always going to have some fundamental lossiness.
Well, that's great point. So the krypton chloride system still has room to grow and improve. There's definitely no doubt about that, especially as we scale up to higher power sources, which we're going to need for larger systems. Right now, the technology is probably good for a small groundwater system, maybe a small community, slower flow rates, few gallons per minute, but we can't treat water, at Orange County necessarily right now with that technology. But there are opportunities for scaling that up to a larger kilowatt-based systems. And at that scale, the efficiency should get much better as well.
Interesting.
And that's why I'm really excited about this phosphor lamp, which has similar technology to the low pressure mercury lamp, which also uses phosphors.
Yeah.
But we got this 30% efficiency and a lot higher output. And this is just the first generation, literally in a lab out of Rutgers that we're looking at. So we think there's a lot of room to grow here as well.
Very cool. Very cool. Well, I've got more questions, but I want to turn it over to Adam Attia. Adam, we're going to try to unmute you so you can ask your question directly. Adam, can you hear us?
Yes, I can. Can you hear me?
Awesome. Great.
Yeah. Hey, great presentation. My first question was just around the placement of the technology, putting it before RO, as opposed to on the RO permeate, more typical. And I understand why, but I'm just wondering if you kind of delved into the effects on energy consumption and cost when you put UV before RO, because you're treating a larger volume of water and UVT is lower. Right. So I just
Totally.
wanted to
You're
get your thoughts
absolutely
on
right.
that.
Yeah, absolutely right. I mean, if we were treating water after RO, it would be very smooth sailing, honestly. But we may not have that nitrate present either. We kind of want that dirtiness for the 222 because some of that, those quote unquote pollutants actually are driving the treatment. Plus, our whole premise here is to can we reduce the fouling on RO membranes? And we had this idea because we saw the transformations of organic matter that we were able to achieve. And in the interest of NAWI's objective of improving membrane-based treatments, we really felt that UV does have a role, and it hadn't really been exploited to the extent possible, mainly because it was limited to the 254 technology. But the 222 stuff, we saw we can get really interesting photochemistry, and without adding the peroxide, that we thought it was worth a shot and seeing if we could characterize the organic changes. But you're certainly right; it would be way cheaper and less energy use because we're able to penetrate those photons way more at a highly transmissive water after RO. And that I think would work as well. And honestly, we haven't done that electrical energy calculation at that stage. But if we need to add peroxide, that would be kind of a neutralizer in that case. But we certainly know under clean water systems that this 222 technology works amazingly well as well. And we've had a bunch of publications out on looking at clean waters and groundwaters and those types of approaches too.
How's that, Adam?
That's great. Thank you.
You can go ahead and ask your second question.
The other one was a little more straight to the point. Do you have remote monitoring capabilities for your existing experimental system?
Existing system, I mean, certainly have the capability. We haven't set it up. I mean, the nice thing about UV treatment is it's all electrons and electricity and signals, and we can definitely put monitors and sensors and follow and track the treatment quite well. So I think one of our dreams is to have these systems be, imagine if you could have a system that wouldn't need any chemical inputs, that you could remotely operate through telemetry and understand how it's working all the time. The dose that's being delivered, the flow rate. You have sensors of UV light in there, and you can actually have a treatment system that doesn't really need much hands-on work, and it can be put in areas that maybe just have solar power that are running the electricity, so running off renewables. And that's really, I think, what we see as one of the first adoptable areas for this technology is in smaller systems that have the need to have lower chemical inputs, less high touch for treatment, and we can drive radical base reduction as well as high levels of disinfection.
Very good. Everybody, I've got more questions, but anybody else, go ahead and raise hands, or you can type it into the chat as we go along. Carl and Tony, so correct me if I'm wrong, but aren't we going to try to put the 222 into Zahi's DPR trailer, and what is the thought about that?
So Zahi's DPR trailer currently has an LED-based technology system, which is emitting at 280
Yeah,
as well as 254. So right now we're looking at those two
280
systems.
versus 254.
Yeah.
Yeah.
And we definitely hope to put it into Zahi's trailer using this 222 technology.
Yeah.
And we're kind of delaying a bit to see if we can get this other kind of multi-wavelength, dual wavelength system in there.
Yeah.
So, but we have a system that has a small flow right now. And, I think, really would be really interesting, but we want to make sure it's mature enough that we got the hydraulics correct. We've got the system designed correct. Because, this system design I showed you before, it doesn't have much engineering, powerhouse behind it. We just kind of threw it together and said, this makes sense.
Yeah.
But we really want to optimize that design before we're going to compare it side by side to a 100-year-old technology that's been out there.
Sure. Very good.
But for sure, we're hoping to put it in that trailer. Definitely, we're working closely with Zahi now. One of my other students, Ryan, is doing that pilot work. So it's an awesome project as well.
It's interesting using the ambient nitrate as essentially an oxidizable source, a source of oxidant. It reminds me a little bit. I saw these very small wellhead water treatment schemes in Israel where they take the raw groundwater, which has a little salinity, they electrolyze it, and that actually creates a chlorine residual. They can create a hypochlorous acid.
Electrochemically.
It's kind of
cool. That's what we're talking about with the project with David Sedlak, is really coupling our his electrochemical system with a UV system and having this kind of fully autonomous kind of system that doesn't need any chemical inputs.
So I want to pivot, and again, anybody else welcome to chime in. DPR regulations are by design varying by state, and every state's coming in with an approach, et cetera, et cetera. And California has just adopted its standard, and its standard is very high and very canonical. Thou shalt do this treatment step, then this treatment step, then this treatment step. And so it's like kind of less of a question, but more of a like, okay, you flip around the treatment train for the benefit of maybe, efficiency and reduce fouling. But I'm thinking like in California, I don't know the answer to this, but what's the journey that we have to take? If this 222 lamp, or even that fluorescent lamp really looks good, I guess in California, our only option is to plug it into a treatment train that's already compliant, and you're just going to get more, I don't know, more bang, but more buck. So it's just kind of interesting to ask how should we expect DPR regulations to adapt as technology improves, right?
Yeah, maybe Tony, you want to take this? I mean, thinking about, are we making improvements in fouling, and will that help drive regulators to say, hey, this might be a viable thing to consider?
Yeah, I think it's definitely something that we have to just make the case for if it seems like it's promising. And I agree that the next step is doing pilot testing, because I think everybody needs, I would also want to see the pilot testing to really be convinced with it. And so I think that's probably the next step, is just trying to build kind of a case for it if we think that this is a good option moving forward.
Yeah. I mean, as I said, in California, by law, you're still going to have the UV AOP unit at 254. You're going to have that technology. So this would plug in as just an add onto that.
Well, I was thinking, I mean, 254 having AOP before or after the membrane, I mean, maybe that would be acceptable as long as we have the AOP. Because the main thing with the AOP,
no. This is California.
No, I hear you.
Really?
I know there's no exceptions. But just think it through. I mean, we want to get 1,4-dioxane reduction. We want to get NDMA. We want to get any byproducts that are forming. I mean, the RO system actually after UV actually is almost a preventive measure to like kind of take out anything that may be weird that's
you
forming.
Didn't kill, right? You didn't zap.
Yeah. And interesting thought at least. But of course, it takes decades to work with the regulators sometimes, so we'll have to work on that.
So just maybe kind of final question for me. We talked about this in the beginning about what was driving the development of the 222, and you got these other sorts of things. Does water treatment, is it is it going to continue to drive innovation, or are we always going to be left with kind of like the incidental byproducts of another industry driving UV lamps, to greater energy efficiency, et cetera, et cetera?
Good question. I'd love to hear from Tony how that's worked with membranes. What's driving that? I mean, I think industry certainly has to drive it. In addition to the water utility opportunities, because the market, as far as water utilities go, is pretty huge. I mean, we can maybe work with global water intelligence to kind of figure that out, but
Yeah.
I don't know if that alone is gonna force major efficiencies in lamp technology, for instance. I mean, we need a good investment in that. We're working on some larger ideas for projects, that would help to move the technology forward. But specifically, obviously, the benefits to energy savings and efficiency at the water treatment side could be huge.
Yeah.
But I don't know, Tony, how has it worked with membranes? I mean, what's been driving? Is it water systems that are driving it? Or is it?
Yeah, I mean, for us, I mean, we do some early stage technology development for membranes, and I think it's just about finding some market that can embrace it. So we have some other work with membranes, and we found, there's sectors that aren't as regulated as drinking water treatment. They're willing to pay for high quality water in manufacturing and so on. And so this is a good place to kind of also penetrate and build a case for new technologies, people that are willing to spend a bit more and have less rigid standards than California.
Yeah, very good. Very good. All right, well, gentlemen, thank you again so much for the great presentation today and for bringing us up to speed on the current bright future of UV disinfection. So from all of us at NAWI, thank you again for tuning in, and for those of you listening to recording. For those of you who can provide your last hour and credit your last hour in our cost share, we'd be grateful for that. But other than that, we will see. But Carl or Tony, are you going to be at WebTech?
I don't know WebTech directly. No,
Okay,
maybe someone
very
from
good.
our group, but not us yet.
Okay, but then we will see you at the NAWI meeting or other meetings
For
coming
sure.
up. And so from all of us at NAWI, everybody have a great long weekend ahead, and we look forward to seeing you on our next NAWI webinar series. Bye-bye, everybody.
Thanks, Peter.